Hi, this is Coach Dorf. We're going to look at another homework problem from section 5.2. In this one, we're given a function capital F equals this integral, and then we're given some values of capital F, and we're supposed to determine which of the values is the largest. Now, the first thing I think about when I look at this problem is this function capital F looks a little weird. What does it represent? Well, it represents the integral, where my variable is that x on the top of that limit of the integral, and it varies with different numbers. And I want to find, what does the integral represent? It represents area under the curve. So capital F I can think of as area under the curve, going from 1 to my variable x. So let's look at some examples here. So first of all, what's f of capital F of 1? So that means I'm going to take my integral. I'm going to start at 1, and I'm going to end at my x value. My x value here is 1, so it's going to look like that. And then I have little f of t dt. Now, don't worry that I have t's and dt there. It's what we call a dummy variable. It could be anything. It could be f of s. It could be f of smiley face. It could be f of Christmas tree. It's just a placeholder there. So I'm going to try to figure out the area for capital F of 1. I want to find the area under the curve where x goes from 1 to 1. Well, if I look at my image here, here's 1. So if I'm going from 1 to 1, it's the area under that curve. Well, the length of that is 0. If I make a rectangle there, it's 0 because I'm going from x equals 1 to x equals 1. So this would be 0 right there. Let's try another one. What if I did f of 2? So that's going to be the integral from 1 to 2, because I put my variable is x equals 2. So I put a 2 at the top of there, and I do f of t dt. So now, if I do this in purple, I am going from 1 x to x equals 2. So that's that area right there. And that number is, I don't know what it is, but it's greater than 0. It looks like it's going to be less than 1, but it's still greater than 0. Let's try another one. Let's do f of 0. We haven't done that one yet. So that's the integral from 1 to my x value, which is 0, t. Now, the first thing I notice here is I have a smaller number on the bottom of my integral sign and a larger number. Sorry, I have a larger number on the bottom of my integral sign and a smaller number at the top. So if I rewrite so that I have the smaller number on the bottom and the larger number on the top, those would only be equal if I put a negative out front, because I've changed the order of the numbers on the integral sign. It's now negative the integral from 0 to 1 of f of t dt. But this is useful because now I can think of it as the area underneath the curve from 0 to 1. I have to have it in that order from smallest to largest in order to think of it easily in terms of area. So let's see, what would that be? So that's going to be this area here. That's going to equal negative area, negative positive area, positive area. So that's also going to be less than 0. I hope that makes sense. I've got the negative sign. It's a positive area there from 0 to 1 because it's above the x-axis, but I have a negative sign out there, and that's what's going to give me this negative, that positive area. Keep working on these. What about f of capital F of 3? So that's the integral from 1 to 3 of little f of t dt. So there I'm going from 1 to 3. So I've got the area. This is really, I can think of this as the same thing as the area from 1 to 2, f of t dt, plus the integral from 2 to 3 of f of t dt. Well, if I look at these areas, there's the area from 2 to 3. The area from 2 to 3, it looks like it's a larger area than the purple area from 1 to 2. But the area, the red area from 2 to 3 is below the x-axis. So that's a larger area that we're subtracting from a smaller positive area that's purple. So all that will also be less than 0, because the positive area from 1 to 2 of f of t dt is smaller than the area from the integral from 2 to 3 of f of t dt, which is negative. So I have more negative area there from 2 to 3 than I do have positive area from 1 to 2. So that's all going to be negative. Let's see, we have two more values to look at, f of 4 and f of 5. So here's f of 4. So f of 4 is going to equal the integral from 1 to 4 of little f of t dt, which I could write as the integral from 1 to 3 of f of t dt plus the integral from 3 to 4 of f of t dt. Now, what do I notice here? Well, I notice that the area, the integral from 3 to 4 here, which I'll do now in blue, that area there, that's negative because it's below the x-axis. And I already knew that this equals f of 3, which is less than 0. So I have something negative and I'm adding more negative to it. So this is definitely negative. And then the last one, f of 5, so that's going to be the integral from 1 to 5 of little f of t dt. And that's going to be the same thing as doing the integral from 1 to 4 of f of t dt plus the integral from 4 to 5 of f of t dt. And I already knew that this was negative. This is because this is f of 4, so that's negative, plus this, which is also negative. And I guess just to keep everything in the same pattern, I'm going to put a color to this, put that as pink. I don't know if you can see the difference between the pink and the red, but it's right there. And that's negative. So this is all going to be negative. So what do I learn here? Well, f of 3, f of 4, and f of 5 are all negatives. So this is negative, this is negative, that's negative. F of 0 was negative, f of 1 was 0, and f of 2 was positive. That's the only positive one. So my answer is f of 2. Hope that helps.